Hi everyone, it's Professor Sansom. I just wanted to finish up a few slides from lecture today to make sure you guys understand how to do some of these calculations related to colligative properties. You should know that I spent time in class working on the concepts related to this because it's more important to me that you understand what's happening at the molecular level and how that manifests in the properties that we observe than it is that you can do these calculations. That said, you do have to be able to do the calculations, so I'm going to make sure that I show you how to do that. Reviewing what we talked about in class today, remember that when we have a pure solvent, there will be a vapor pressure above the solvent where some particles are evaporating and some are condensing in equilibrium. So the question is, what happens if we now have a solute dissolved in the solvent? This is an example of sodium chloride being dissolved in water. You can see if you look at the surface of the liquid, the solvent particles won't have as much access to the surface of the liquid because the solute particles are taking up space, and therefore fewer particles will evaporate, and the vapor pressure will be lowered. Now we saw in class today that we can use Raoult's law to calculate vapor pressure lowering, and we saw this for volatile solvents. And in the case of volatile solvents, we had to take into account for the total vapor pressure, the contributions from the solvent with our Chi1P1, that would be for our water, Chi2P2, Chi3P3 for each solute that's dissolved. Now we're going to talk about non-volatile solvents, and in this case we only have to take into account the mole fraction of the solvent itself and none of the solutes because the solutes won't contribute to the vapor pressure. Just be careful when you're doing this that you take into account that there may be multiple moles of solute. So when you're calculating your mole fraction of solvent, you need to calculate the total number of moles of dissolved particles. Now we'll look at some calculations practice for this. So we have a problem here with glucose. We have 360 grams of glucose. The molar mass is 180 grams per mole. So we know that that's actually going to be 2 moles of glucose. We also have 360 grams of water, and we'll use the molar mass of water to calculate the total number of moles. That's 20 moles of water. Because glucose doesn't dissociate, we just have the 2 moles of glucose and we don't have to think about additional moles because of dissociation. So our mole fraction of water is going to be 0.909, and the vapor pressure above the solution will be 28.9 torr. Notice the vapor pressure above the solution is lower than the vapor pressure of the pure solvent. That is the phenomenon of vapor pressure lowering. Now we have a practice problem that we'll look at. We have a solution of sodium chloride in water, and it's at 25 degrees, so we know the vapor pressure of water at 25 degrees is 23.8 torr. We have to remember that sodium chloride is going to actually dissociate into 2 moles of ions. So when we calculate from our mass, we get the number of moles. We have to multiply by 2 to get the total number of moles of ions. This is important so that we get the right mole fraction. Now our water we can turn into moles as well using the grams and the molar mass, and then we'll take the mole fraction, 0.947, and then to find the vapor pressure above the solution, all we do is multiply our mole fraction times the vapor pressure of the pure solvent. And we see again that our vapor pressure above the solution is lower than the vapor pressure of the pure solvent. Now if we look at our phase diagram, we can see that the pale red line or pink line shows us the vapor pressure of water at various temperatures and pressures. If we follow this down, because the vapor pressure is lowered, the boiling point is elevated. In other words, it's going to require more energy to evaporate those solvent particles that don't have the same access to the surface that they would in the pure solution, in a pure solvent. Now, this same phenomenon affects our freezing point. If we think about the molecular level, we can see The triple point is going to be adjusted here as we follow this line down. And if we think about the molecular level, and we think about freezing, we can also see that solute particles would disrupt the formation of crystals in the solid phase, and so our freezing point will be lower than it would have been in the pure solvent. So now if we look at this phenomenon of boiling point elevation, we just need to recognize that we can't use molarity because molarity will actually vary depending on the temperature because it's based on the volume. As the solution becomes hotter, it becomes less dense, so molarity can vary significantly. Instead, we'll use molality, which is a different measure of concentration that will not change when the temperature changes. Molality, it's symbolized by this lowercase italicized m, is defined as the moles of solute per kilogram of solvent. This is different from molarity in two ways. First, it uses mass in kilograms instead of liters, and second, it's only the solvent and not the solution. Okay, so let's do a practice problem for molality. Just calculating molality is pretty straightforward. If we know the molarity of the solution, we have to just assume that we have 1 liter. So in 1 liter, we would have 1.46 moles of NaCl. We'll use the molar mass to convert that into grams of NaCl. Even though the grams of NaCl aren't necessary for the molality, they're necessary because we have to subtract them out of the total mass, which we calculate using the density of the solution. And so once we have the total mass of our 1 liter of solution, again, we just assumed that we had 1 liter. We could have assumed some other volume, but 1 liter is easy. And now we know we have 1,292 total grams, but what we need is the mass of just the water, because remember, molality is divided by the kilograms of the solvent. So we subtract these two, and we'll end up with 1,207 grams of water. Turning that into kilograms, we calculate our molality, 1.21 molal. We can now get back to our original point, which was calculating the boiling point elevation for a solution. Solutions are always going to have a higher boiling point than a pure solvent, and we'll measure this with our delta TB, the delta triangle symbol meaning a change in the boiling point. The equation has I, which is the Van't Hoff factor, Kb, which is a constant for the solvent, and m, which is the molality of the solution. So our final boiling point will actually be the original boiling point plus the change in the boiling point, that is the increase. Let's do a practice problem for this. We'll use the same solution we were just working with, a 1.21 molal solution of sodium chloride in water. The Kb for water is 0.512 degrees Celsius per molal. And that's a constant for the solvent. We'll go ahead and plug in what we have, noticing our I here, the Van't Hoff factor, is 2, because NaCl dissociates when you put it into water into 2 ions. And when we calculate this, we'll see the change is 1.24 degrees Celsius. So my new boiling point would be the original boiling point 100 plus 1.24, so 101.24. Now, why does this matter? It's vitally important for our supplies of maple syrup and our breakfast enjoyment. Because actually, when they're making maple syrup, they take this sap from a tree, which has about 1 or 2% sucrose. They boil off the water to concentrate it, and they have to get to 67%. Apparently, that's when you have the best maple syrup. And they can measure this based on the boiling point. They'll know they're at 67% when the change in the boiling point is 7 degrees. So now we'll investigate the other colligative property that we're going to talk about today, which is the freezing point depression. We already talked about why the freezing point is depressed when we have a solution, and the equation is pretty much the same as the boiling point. except the Kf value will be different than the Kb value. So you have to just make sure that you're using the right constant when you plug into this equation. The other thing that's different is that because the freezing point is depressed, when we calculate our freezing temperature, we'll take the original freezing temperature and then subtract the change in the freezing temperature, and that will give us our new freezing temperature. So we'll go ahead and do a practice problem for this, calculating the freezing point depression. This is important because we actually use this colligative property in the winter when we're salting the roads. Magnesium chloride is a common salt that's used in the winter to lower the freezing point of ice that's on the road to make it liquid again. So this question is asking us what mass we need to add to 1 kilogram of water to lower its freezing point by 5 degrees Celsius. Well, we know what the delta TF is going to be. We know what the I is going to be for magnesium chloride, and we know what the Kf is because we can look that up. And so the thing that we're going to be solving for here is the molality. We'll use the molality to find the grams that we need. So remember, when you're doing this, our I for magnesium chloride is going to be 3 because there are 3 ions. It dissociates into 1 magnesium ion and 2 chloride ions. When we solve for the molality, so this is just the molality here, and we'll have 0.896 moles of magnesium chloride per kilogram of water. We can just turn that into grams. So we have a quick iClicker quiz just to make sure that we understand the influence of the Van 't Hoff factor. If we look at sugar, we know that the Van 't Hoff factor would be 1 because it doesn't dissociate when it dissolves in water. Sodium chloride, on the other hand, would create 0.02 molal of ions in water because the sodium and chloride dissociate. And calcium chloride would make a 0.03 molal solution because it separates into a calcium ion and 2 chloride ions. The last thing that we'll do is just a quick summary at the end of the day, explaining why vapor pressure is lowered when a solute is dissolved in a solution, comparing and contrasting vapor pressure lowering with volatile and non-volatile solutes. Both use Raoult's law, but it's a slightly different form, and explaining why a lower vapor pressure causes boiling point elevation. I'd like you guys to do those on your own. Make sure you understand those concepts so you're ready for our next day and ready for the exam.